refer to another very interesting problem on mechanics. Here we have a rope, a uniform rope. Uniform rope means mass per unit length is constant, AB, right? And it's fixed to a nail at A on the wall and to a nail at B on the ground. But no part of the rope either touches the wall or touches the ground. That's given in the problem, right? And it is found that the tangent to the rope at A, makes an angle alpha with the vertical. The tangent, this is the tangent to the rope at A. The rope assumes a shape, and we will learn down the line in mechanics that this shape for a uniform rod is called a catenary. It has a special equation. We will not discuss that right now, but the shape is called a catenary. The shape is called a catenary. Now, the tangent at A is known to make an angle alpha with the vertical, and the tangent at B, this is the tangent at B, this end of the rope makes an angle beta with the vertical, right? And mg is the total weight of the rod. We want to check on the following: whether the horizontal component of the tension, see there is a variable tension along the rope from A to B. There is a variable tension. We want to check if the horizontal component of the tension force is uniform along the rope. That's one. Second, we want to check if the vertical component of the tension force increases with height when we go from B to A. These are the two things whose validity we need to check. So first of all, let me draw the free body diagram of AB, right? Now at A, there is a tension. I'm drawing the free body diagram at A of AB. At A, there is a tension TA that makes an angle alpha with the vertical. The tension will always be along the tangent. That makes an angle TA with the vertical. TA could be resolved vertically as TA cos alpha and leftward horizontally as TA sin alpha. And let's say the tension at B is TB, which is tangent to the rope at B, right? And this TB makes an angle beta with the vertical. That's given. Right? Tension will always act along the tangent from point to point. So if I look at the free body diagram of AB, at A, the tension will act like this. At B, the tension will act along the tangent in this direction. Now, TB could be resolved as TB sin beta rightward and TB cos beta downwards. Now, we need to check the horizontal component of the tension force along the rope. When I go from B to A, I look at a certain point C. Which is at a height h from the ground. And I want to look at the free body diagram of BC. So at B, like I said, there is force TB, which could be resolved as TB sin beta and TB cos beta. At C, let's say the tension at C will be along the tangent at C. Which is along the tangent, which makes an angle, say, theta with the vertical. This tension could be resolved as a vertical component TV, which is TC cos theta, and a horizontal component TH, which is like a TC sin theta. And there is weight of BC, right? So obviously, as you keep moving up, the weight mg will increase with h. Mass of BC will depend on h. Now, look at AB first. There is equilibrium of AB. Let me write down the equations for AB. There is equilibrium for AB. That means the horizontal components will cancel off. That means 1, TA sin alpha will be equal to TB sin beta, right? 2, the vertical components TA cos alpha, mg and TB cos beta must take care of each other. So that means net vertical force, which is TA cos alpha, must balance mg plus TB cos beta. Now one thing that you can see, TA sin alpha is the horizontal component of tension at A and TB sin beta is the horizontal component of tension at B. They are equal. So that means at the extreme ends, B and A, the horizontal components of tensions are equal, right? Now let me look at C. For equilibrium, horizontal and vertical forces must cancel off. So very clearly, TH must take care of TB sine beta. And TB sine beta is a constant. That means the horizontal component of the force didn't depend on BC, didn't depend on where C was selected, right? So that means the horizontal component is uniform. So option A, the horizontal component of tension is uniform. It's the same for all C's. Because see, the horizontal component is TB sine beta and TB sine beta are fixed numbers. TB is the tension at a fixed point B, sine beta. Beta is the angle that the tangent makes with the vertical at the end B. So this is a constant. That means TH is constant. That means the horizontal component of tensions will remain uniform. So this is true. Vertical component of the tension force increases with increase in height. What about the vertical component of the tension? So let me look at the vertical component of the tension at C. For equilibrium of this, what can I say? TV, vertical component of the tension, will be, this is mg of BC, right? Weight of BC. So mg of BC, weight of BC plus TB cos beta. Now, nothing happens to TB cos beta because this is about a fixed point B, but mg, mass of BC, will increase with height. As I take greater and greater heights, the weight of BC, this is the weight of BC, will increase. So this part will increase. So TV increases as H increases. That means when I go from B to C, the horizontal component of the tensions will remain the same, whereas the vertical component of the tensions will increase. Now, can alpha be 0? No, alpha cannot be 0 because if alpha were to be 0, then beta would have to be 0 too, or TB would have to be 0. Realize one thing, that alpha cannot be 0. You might want to think about it. Alpha cannot be 0. So this then is again an interesting situation, but a whole lot of interesting things around the catenary, which is the shape of a uniform rope, can be obtained. But this then, if you understand, you've got the foundation right. But this much for this problem. Now, so much so far. I couldn't resist sharing another problem with you on Newtonian mechanics, and I think a very fine problem in terms of, all that it bundles in one place. So let me share the problem with you first. So what we have is a small metal ball. This is the small metal ball, and you can say it's of mass m. All right, is being pulled on a fixed frictionless hemisphere. This is a fixed frictionless hemisphere, right? And there is this pulley whose radius is negligible. There is this metal ball whose radius is also negligible. You can treat this like almost like a point mass. Compared to the radius of the sphere, compared to the radius of the hemisphere. Now, as the ball slides from the bottom to the top, as this ball slides from the bottom to the top, from this point it slides to the top. We want to figure out, and the whole thing is pulled very, very slowly. That means the whole thing remains unaccelerated at all times. That means essentially in equilibrium from instant to instant. When very slowly means essentially in equilibrium from instant to instant. Now, as the ball slides from the bottom to the top of the hemisphere, how do the magnitudes of F, and the normal reaction R between the ball and the hemisphere change with time? So, let me call small r as the radius of the hemisphere, right? Because capital R I have designated as normal reaction. So now, let me look at an intermediate state of the particle of mass small m here, right? If it's being pulled with a force F, the tension in the string is going to be F. Now, let me draw the free body diagram of small m at this instant, when it's at this point, and designate this instant with the radius small r, making an angle theta with the horizontal. This theta is varying from a certain value theta naught to the topmost position where theta becomes pi by 2. At the topmost position T, theta will become pi by 2. So theta is varying. P is the position of the pulley. The point joining the particle Q, to the pulley P makes a variable angle phi, and this need not be along the tangent at Q. So now force is acting on Q at this instant, right? I want to, so there is tension F, which is variable. It's varied to keep it in equilibrium. There is weight mg and there is normal reaction R, which would be in the radial direction. The radial direction in a hemisphere, sphere, any circular shape would be along the radius. The normal is perpendicular to the radius is perpendicular to the tangent, and therefore this is treated as the normal direction at the point Q. Now realize that if this is phi, F makes an angle phi with the vertical. This is R, which is along the radial direction. It makes an angle theta with the horizontal. These are the angular dispositions, as you can see, right? At this instant of time then, for equilibrium, so there is normal reaction R, mg and F. Let me write down the equations for equilibrium vertically and horizontally. In the vertical direction, do you realize there is R in this is theta, so this will be 90 minus theta. So R in the vertical direction is R sine theta, right? Plus F in the vertical direction is F cos phi, and that must balance weight mg. That's equation 1 at this intermediate instant. In the horizontal direction, realize this is phi, so this is 90 minus phi. F has a vertical component F cos phi, but a horizontal component F sin phi. F sin phi is equal to R cos theta, That's equation 2. So one thing, I can solve for R and F in terms of theta and phi. Let me do that first. So what I'll do here is I'll write, say, F as R cos theta by sin phi. So R sin theta plus F, which features here, I'll write as R cos theta by sin phi. The F here I write as R cos theta by sin phi into cos phi, F cos phi equal to mg. That is, from these two equations I have eliminated F. So let's see what it turns out to be. R then is like cos theta cos phi plus sin theta sin phi, cos theta cos phi plus sin theta sin phi equal to mg sin phi, right? What does R turn out to be? R then turns, see, realize cos A cos B plus sin A sin B is cos of A minus B. So this is cos of theta minus phi. So R then becomes mg sin phi divided by cos theta minus phi. Yes or no? So that's as far as R is concerned. What about N or F? F then turns out to be R cos theta by sin phi, right? F turns out to be R cos theta by sin phi. I can plug in R from this equation and obtain, but I'm still not done. Let's do some geometry here. Look at this triangle QPO. Q is the point where the particle is kept, O is the center, and small r is the radius. OQ is going to be small r, which is fixed, and OP, which is the height of the pulley from the base, which is h, that's fixed. This angle, as you can see, is phi, and this angle, as you can see, if this is theta, this is going to be 90 minus theta, as you can see, and this angle alpha would be 180 minus this plus this, 180 minus phi minus 90 minus theta, right? Which turns out to be, as you can see, 90 plus theta minus phi, that's alpha. Now, if I apply sine rule to this, do you see that h divided by sine alpha equals small r divided by sine phi. Small r divided by sine phi, right? And what does small r by h turn out to be? Small r by h turns out to be sine phi divided by sine alpha. Small r by h turns out to be sine phi divided by sine alpha, where alpha is 90 plus theta minus phi. You know what I did here? Small r by h is sine phi, which is this, divided by sine alpha. Sine alpha, alpha as we have seen here, this angle is 90 plus theta minus phi, right? So then, what is small r by h? Small r by h is sine phi. R and h are constants. Sine phi divided by sine 90 plus x is cos x, right? Is cos theta minus phi. Now that's really the interesting fact here. That means sine phi divided by cos theta minus phi. Sine phi divided by cos theta minus phi is the radius of the hemisphere divided by the height of the pulley. So this is like mg into r by h. R by h. Sine phi by cos theta minus phi is r by h. R is the radius of the hemisphere. H is the height of the pulley above O, right? So that means what? Do you realize mg is a constant? R, the radius of the hemisphere, is a constant. H is a constant. Good. That means what? Normal reaction R. Normal reaction R. Capital R. Normal reaction is a constant. It's not varying. Fantastic. Very counterintuitive. Very counterintuitive. This is not what we expected, but this is how it turned. That's why I found this problem really, really exciting. An interesting situation. So we have a rope AB, and there is a longitudinal force F, horizontal, applied on the rope, and it's resting on a smooth horizontal surface. The rope is AB, right? This end is x equal to 0, and at x, this becomes, let's say, x equal to the length of the rope. Now it is found that when this is done, tension or the tensile force is measured starting from x equal to 0, which is the end A, to the end B. The tensile force is measured, and this is the graph of the tensile force or the tension that builds up in the rope as a function of its distance from A. Now we want to make a conclusion about the linear mass density of the rope. Mass density is mass per unit length. Mass density is mass per unit length. Linear mass density is lambda x, which is mass per unit length at x. Mass per unit length at x. This is what it means. That means, you know, if at x I take a small element of length dx, that means at x this would be x plus dx, then the mass densities over the small region would be lambda x. Then that means the mass at this of this element would be lambda at x into dx. Lambda at x into dx. Over this very small dx, lambda does not vary. Lambda will be the same as lambda at x. Now, what is it that we need to do? We need to make a remark on the linear mass density starting from x equal to 0 to x equal to this point, given that this is the tension that develops in the rope as a function of x. Now if I look at from the end A, if I look at an element of the rope at x, and this is x plus dx, a segment of length dx of the rope measured from A, this end of this segment is at x, and this end of the segment is at x plus dx. Now, what can you conclude about the tension that develops in the rope as a function of x? So, 1, the tension at this x would be tension at x. Tension at this end of this segment is going to be tension at x plus dx, right? And the difference in the tension, this minus this, is going to be dt. The change in tension from x to x plus dx is the change in tension or the tensile force. That must be the mass of this. What's the mass of this? The mass of this is lambda at x into dx. That's the mass of this into the acceleration of this segment. Now, the acceleration of every segment will be the same as the acceleration of the bigger rope. And what's the acceleration of the bigger rope? Is going to be F by m, which is going to be the acceleration of every segment, So this is going to be F divided by the total mass of the rope. That's going to be the acceleration, right? So again, as you can see, dt dx is F by m into lambda at x into lambda at x, right? That's the rate of change of tension with distance x from this end. Now, do you realize what is happening to dt dx? See, f by m is a constant, so I can say this is like c times lambda at x. F by m I choose as some constant c. F is the force, m is the total mass of this rope. Now, would you not want to be, what's happening to dt dx? If we know the trend of dt dx, I would know what is happening to lambda at x. So dt dx is the slope of the tension versus x graph. This is dt dx. Slope of this line will give me dt dx at x equal to 0. The slope of this will give me dt dx at this point. The slope of this will give me dt dx at this value of x. And so on and so forth. So do you realize that the slopes of the tangents is decreasing? The slopes of the tangents is decreasing. That means dt dx, which measures the slope of the tangent at any given x, dt dx, because the tangents are becoming more and more flat, so dt dx is very clearly decreasing with x. If dt dx is decreasing with x, obviously lambda must be decreasing with x. So linear mass density is decreasing with x. It's the highest at x equal to 0 and the smallest at x equal to x of p. Yes or no? So again, I think it's a good problem to look at. Interesting. There is combination of graph and analysis. So I think, you know, once you are past this problem, you would feel good about it. Thank you so much. Bye-bye. But interesting. We have a pipe of a weird shape shown. This is AB, a pipe of a weird shape. And inside the pipe, there is a rope PQ. The shaded region is a rope PQ, uniform rope PQ of mass M and length L. This is a rope PQ of mass M and length L, resting inside the tube, And the whole unit is in a vertical plane under the influence of gravity. The whole thing is in a vertical plane under the influence of gravity. The coordinates of P are x1, y1 and Q x2, y2. That's given. P has coordinates x1, y1 and Q has coordinates x2, y2. That's given in the problem. We want to find an expression for the total frictional force that the tube exerts on the rope PQ. We want to find the total force that the tube exerts on the rope PQ to maintain it in equilibrium, right? Now what I do is, surely you know the shape will not matter. The weird shape that is given is inconsequential. What I do is, say I take a small element of the ropes anywhere. Say I take a small element of the rope ds, right? And say this is dy, change in y, this is dx, change in x. Small element of the rope ds somewhere in the tube, right? And say this angle is theta. This angle is theta, right? And let's say rho is the mass per unit length. So this is the length of the rope. Rho is the mass per unit length of the rope, which is given to be uniform. Mass per unit length of the rope, right? So what's the mass of this ds? The mass of this ds is going to be rho into ds, right? Rho into ds. And would you not want to believe that eventually there is dmg acting downwards, vertically downwards under the influence of gravity, and this can be resolved as dmg sine theta. So this is ds. dmg sine theta is the component. dmg sine theta is the component of dmg along the length ds, along the length of the rope ds, right? And of course there is dmg cos theta, which we are not bothering. That will be taken care of by the reaction from the tube. Now the frictional force acting on it, df, would just about balance this weight, right? So df will take care of the weight, dmg sine theta, right? But what's dm? Dm is rho into ds. So rho g ds sine theta. Dm written as rho into ds. So then, but what's ds sine theta? Do you realize ds sine theta is dy? So this is like rho g dy. That's df. The frictional force on this element, the total frictional force would be sum of all of this taken along the entire length of the rope, right? Very clearly, y changes from y1 to y2, y changes from y1 to y2, or y2 to y1, does not matter really. So then the total frictional force F acting on the rope, obviously it has to be like this, right? Is going to be rho g into change of y. Rho g into change of y. See, this y is higher, so y1 minus y2 is what we can say. So this is like rho, which is mass per unit length. Mass per unit length means m by L into g into change in y. Change in y is y1 minus y2. That's the total frictional force. That's the sum of all the friction acting at every single element that constitutes this rope PQ. Yes or no? So I thought this was a neat little problem, and it could actually surprise a lot of people. It might initially look really complicated, but that's not to be. It's really as simple as this. Thank you so much. Bye.